Hello, everyone, and welcome to today's JMP Academic webinar, the second webinar in a two-part series on using JMP's teaching and learning resources. I'm Ross Matuslam. I'm an academic ambassador at JMP, and I'm just here to host and answer questions in the Q&A today, while my colleague, Kevin Pochner, shares with us a number of freely available resources from the JMP team that you can use to enrich your course if you're teaching statistics or some related topic with the JMP Student Edition statistical software. So 2 weeks ago, some of you may remember, Kevin showed us a number of resources. So we saw the Learning Library, which is a collection of quick tutorials for how to do certain things in JMP. We saw the Case Study Library, which presents real-world data analysis scenarios with their multi-step solution paths and exercises. We also saw the enhanced data sets. So these are data sets that come with documentation providing a backstory and motivation, data dictionary, and exercises. And we saw a few others as well. And today, Kevin's going to show us several more. But again, all of these being teaching and learning resources that we provide at JMP to help you enrich your course. Now, before we get started, I just want to encourage everyone to ask questions at any time throughout the webinar. If you do, please just type them into Zoom's Q&A panel. And I'll be in there answering questions as Kevin goes along. And then Kevin can also pause and take some questions live as well. Now, feel free to use the chat if you want, just for general comments to us or to the group. But if you have questions, please do type them in the Q&A. It just really helps us better manage the questions and to be able to display our responses to them to you more easily. So even if you don't have questions, go ahead and open up that Q&A panel and you'll be able to see what others are asking and what our responses are. So with all that established, Kevin, are you ready to go?
I am.
All right, feel free to steal that screen share.
Okay. See my screen? I'm just on the course materials page.
Yep, looks good.
Great. Just to direct you to what Ross was talking about. On the last webinar, I presented a bunch of our teaching and learning resources that you can find on our course materials page. One of the items here is our webinar library, which this is where you can find the webinar we did 2 weeks ago. It's right there, and any of the others that we put up there. I can show you how to get there through our website, but if you just go and type into Google, JMP academic webinars or JMP case studies, it will direct you right to it. So it's not hard to find it. Now, what I'm going to do is, I'm going to move this aside for a second. Now, I'm actually going to start off with opening up a data set in JMP. And the reason why is I want to show you this one teaching learning tool we have that you can access through our distribution platform that I really like. So in this example, I've just got this continuous numeric variable. And let's say I want to do a hypothesis test on the mean. So as many of you know that are users, whenever you're doing a univariate analysis, you launch this distribution platform, you put the variable there. It's going to start off with initial report, which in this case is a histogram and a box plot and a bunch of summary statistics. But if you want to do a hypothesis test on the mean, the classic t-test as we often call it, then under the red triangle, you would go test mean. And this one happens to be testing if the mean is 4.35. And when you do that over here on the far right of the report, you'll get the results of the one sample t-test. But the reason why I'm doing this is under this particular red triangle, there are two really great interactive tools. So one of them is this p-value animation. So if I open that up, okay, sorry, it's opening up on another screen, so I have to keep on dragging it over. Okay. So here is this interactive tool where we can help students understand the concept of what a p-value is. So basically, that was the value I typed in for the hypothesis size value. Under the null, this is the mean that we got, the sample mean we got here. This is the standard deviation. This is the sample size. So there I can see my t-test statistic, the standard error, and the p-value. Well, what I can do is I can go in here and change things, or I can grab this and interactively drag it around. So I can say, well, what if the sample mean we got was some other number? And now we can see we're illustrating the concept of calculating the p-value. So, we can start off and we can well, in addition to dragging it over, we can change things like, well, what if instead this result was based upon a sample size of 15, not 30? Now we can see the distribution change. Or what if instead of the standard deviation being 0.04, it was 0.08? Now, what I like to do with students is I always like to put something up like this and say, okay, I'm going to change something, like whether I change the sample size or the standard deviation or the hypothesized value or the value I'm going to get from my data. I'm going to change something, and can you guess what is or isn't going to change somewhere else? And is it going to go up or down? Now, sometimes it's hard to guess exactly how much it's going to go up or down, but students can be pretty good at guessing, well, that value is going to get larger. P-value is going to get larger. The p-value is going to get smaller. And I like that. And when people start getting that intuition and they start seeing, well, actually statistics is more intuitive than initially thought. So this is one tool, this p-value. And when I drop down the red triangle, you might have also seen this one here on power. And so now I can teach the concept of type 1, type 2 error in power. The same thing, I've got my distribution under the null. I've got my distribution under the alternative. And so I can click and drag these around. And so I'm seeing the shaded region for the type 1 and type 2 error. And of course, power, you see the values over here. So I can interactively click and drag this around, or I can go in here and type in and change the numbers, okay? So again, what if the standard deviation was twice as big? What happens? All right, you're going to see those distributions wider, right? And so you're going to see that type 2 error get larger. So again, just a really cool interactive tool that you can access from the distribution platform. So after you run the distribution platform on a numeric variable, do a hypothesis test for the mean, you access this from the results of doing that one sample t-test here. Okay, so I'm going to close this up. And what I'm going to focus on for a good amount of this webinar is the tools that we have under our student menu. Now, if you are using our academic license, okay, so if you went to jump.com/student and you and your students are using that one, which you should be, that's our free academic license, then this student menu is going to appear. If you are from the commercial world, and in other words, you're not using our academic license, then what you need to do is you need to go to our marketplace. And so this is just, if you just type in Jump Marketplace, it will direct you to here. And where is it? There it is. This is a website we have where you can download add-ins and various tools that people get, so you can add to capabilities of Jump. And one of them here is the student menu. You click on this, you'll basically just download it and drag it onto the Jump icon, and you'll now have that menu available. So I'm going to be showing stuff in this menu. Again, if you have the academic version, this is already going to be there. Okay, so I won't be able to show all of the tools here, but I'm going to do enough of a sampling that you're definitely going to get the idea with how these things work. Okay, so I'm going to start off by going into the applets here, and I'm going to do this first one here, this distribution calculator. Okay, so I got to keep on dragging these over from another screen. Apologize for that. Okay, so this is a tool that allows you to pick a distribution, and you can see here that we got a pretty comprehensive list of different distributions. You can specify the parameters. So in the case of the normal, I'm going to have the mean and the standard deviation. If I do the t-distribution, I'm going to get the degrees of freedom. And then over here on the right, I can either provide a value and get the probability greater or less than that. So right now I'm saying, what's the what proportion of that distribution is less than the value 1. So I can go in here and type anything I want. So I'll type 1.5 or negative 1.33. So I can solve it that direction. I can solve it the other way, okay? The proportion of the distribution greater than that. I could choose two numbers. I'll pick 1.33, negative 1.33. And so I can solve for what's the area in the middle or what's the area in the tails. So this tool can take away that process of going in the back of the book. I haven't looked at an intro textbook in a little bit, so I don't know if that's still the method that's predominantly used, but going back to that table in the back of the book, the Z table and the T table, and finding the values. You can use this instead. So if you're sort of manually doing a statistical test, I'll go to a t-test for a second. And let's just say we had a sample size of 25. So then the degrees of freedom is 24. And we're like, okay, so we got let's say you got a test statistic of 1.5, just to pick something. I could type that in, and then right here, now I have my p-value. So this is just, I think, a more interesting way to understand the areas under the curve of various distributions. And again, we have a pretty large collection. So the normal and the T might be what you're using frequently in an intro class, but there's no reason why you wouldn't necessarily be using the others. Plus, they just really help kind of illustrate how the distribution is changing when you change the parameter. So for example, I'll go to the log normal for a moment, and I can sit there and say, well, what if the location parameter is 2? What if the scale parameter is 0.1? And you can start to see how the shape of that distribution changes. And again, you can go down here with all the controls if you want. I'm just using it at the moment to just illustrate the idea of changing different parameters and see how it affects the shape. And this can help you illustrate things like, oh, notice for certain parameters, the log normal actually starts to take on a symmetric shape similar to the normal. So you can choose any of these distributions and change the parameters. Let's go back here. You can also change this where you're typing in the probability and then you're getting the value. So I'll pick something here. Okay, how much of the distribution is less than -2? Whoops. Hope did I do that right? Oh. Oh, sorry. So I'm typing a probability. So sorry. Okay. So if I'm saying, okay, what value is capturing the lower 25% of the distribution? And there's my right answer right there. So again, I can do is a right tail. I can find the area in the center or the tails. Okay, so just a fun way to do this instead of using the table. All right, I'm going to close this up. I'm just looking to see. Okay, no questions coming in. Now, these tools I think are great to teach the concepts, like things like a sampling distribution. I know we explain it, we put formulas up on the board, but I just think interactively trying to understand what these concepts are, I think are a much better way to learn. So I'm going to open up the sampling distribution of the sample mean. So in this tool, you start off with assuming a distribution for the population, and we can pick normal or skewed right distribution. You can even put in your own data if you want, because you want to form a particular shape. But I'm going to start off with the normal. So you're going to define the mean and the standard deviation of that population. So obviously, if I change this, I'm going to see that shape. It's you notice that it could have sort of changed the axis down here. So I can define those parameters. Then over here, I am going to take a sample of some size. So let's say we're going to take a sample of 25. So we're going to take one sample of size 25. And when I click this draw additional sample, it's going to show me a histogram of those 25 observations I just randomly sampled from this distribution. I can see the sample mean and the sample standard deviation. And then down here, down here, it's plotting that sample mean, that one right here, that 100.1. Now, if I say draw another sample, Again, it's going to draw a second sample of size 25 from that population. Same thing, here's my sample mean, sample standard deviation. Here's the histogram, and then it's plotting that next sample mean. Now I can do this one at a time, or I can kind of speed this up by choosing number of samples more than one. So I'm going to pick number of samples of 50. So what's going to happen is it's going to grab 50 samples, each of size 25. And I'm actually going to click this animate so you can actually see it happen. So when I click draw additional samples, you're going to see that here, you're going to see 50 histograms kind of generated really quickly. And then down here, you're going to see each of those sample means being plotted. All right. See how that, so I can keep on going there. Now, a couple concepts that you're trying to get students to understand is that, notice that this is on the same scale, 40 to 160, 40 to 160, right? So this is where you can start explaining the concept of the standard error, right? So you got the standard deviation of the sample means right over here. You can see that that's quite a bit narrower. Obviously, that's based upon the sample size. And you're seeing that it takes on that normal shape. So if you picked another distribution, let's say, I'm going to do skewed right, this same concept. Now I'm going to speed this up. I'm going to do 200 at a time. So this is going to go real fast. And we keep on. So even though that population distribution is highly skewed, that sampling distribution starts approaching normality. Okay, so this could be a great tool to teach the concept of the central limit theorem. And similar to what I said before, what I like to do is I like to change something, maybe change the population standard deviation, maybe change the sample size, and then see if the students can guess how that sampling distribution is going to change. Is it going to get wider? Is it going to get narrower? Now, when I pull down that menu, you might have also seen the sampling distribution for the sample proportion. So this works the same way. I'll just open it up quickly. So you're gonna pick the distribution of the population. In other words, what is the proportion of that attribute existing? So this is just picking 20%. Oh, this one's nice actually because I'm going to pick 20%. Now I'm going to do the same thing where I'm going to speed this up. So I'm going to do 100 at a time, taking a sample size 50 with a population. The proportion of that attribute I'm looking at is 20%. I'm going to animate this again just because I like to see it happen. And so it's going to go through. And so now I'm looking at the sampling distribution of the sample proportion. And what do you know? We're seeing how that approaches normality and the reason why normal procedures for confidence intervals and hypothesis tests work. Again, same thing. You can go in here and change something. Maybe you change the sample size. Maybe you change the population proportion. I don't know if some of you teach this to your students, but where the variance is the largest when the population proportion is 50%. So I can go in here and see, well, what happens in that scenario. And if you kept an eye on the standard deviation or the standard error of that statistic, of that sample proportion, you will see that it will be the largest when you're at 50% versus picking something much lower, much higher. Oh, you know what? Actually, I'm kind of curious. In the chat window, could you just do like a yes or no if you've ever used these particular tools? I'm sort of curious what proportion of the people I'm speaking with have seen these before. All right, a lot of some no's coming in. Good. Okay. All right. So I'm going to close this one. I'm going to look at some more. Oh, this one I like. The confidence interval for the population mean. Okay. The way this one works is same thing. You define a population. So you're picking a distribution. Again, you can pick normal, pick skewed, uniform, or enter in your own data. So I'm going to define a mean and a standard deviation. I'm going to pick a sample size. I'm going to draw one sample of size 25. I got my confidence level, and I'm going to open that up actually as well. And when hold on, I want to make this bigger so you can see everything. When I hit draw additional samples, it's going to take a sample of size 25 from that normal distribution. Here's a histogram, and I've got the sample mean and sample standard deviation. And here is my confidence interval. And then it's plotting that confidence interval right there. And you can see for this particular case, this confidence interval contains 100. So this is an example of, hey, this particular confidence interval correctly captured the population mean of 100. So I can keep doing this. So I'm gonna grab another one. That one, okay, so keep an eye here. You'll see these bars and they'll either be green or red. Green if it captured the population parameter, and red if it didn't. So I can keep clicking along, or I can speed this up and I'm going to say, I'll say 50. So this is going to draw 50 separate samples, each of size 25, and it's going to calculate the confidence interval for the mean. Let me animate it so we can watch it happen. Oh, there's one that missed. There's another one, third one. Okay, I'm gonna keep going. And what I want you to do is keep an eye down here, because this is where you're going to see the proportion of those intervals that correctly captured 100. And what we should be seeing is that should be converging to 95%, because you're trying to get students to illustrate, or illustrating to students. That's what confidence means. So if in the long run, you're expecting that many intervals to correctly capture the mean. Now, in practice, you only get one of them, right? So you don't know if yours is one that has captured the value of the parameter or it's missed, but you're 95% confident because 95% of them in the long run will have correctly captured it. So same concept, which is why I think these tools are great, is change something. Maybe change the sample size, maybe change the confidence level, maybe change the standard deviation, and see if they can correctly guess what's going to happen. I always used to trick students with this one. I would say, well, what if we took more data? Wait, I don't want to pick 50 because it's the same one. Let's say we took a sample size 100. What's going to happen? Well, some students will get tricked and like, oh, well, more data, that must be better. Then maybe more of the intervals are going to be correct. Well, no, we're setting this at 95%. So the same concept is still going to happen. These things are going to converge to 95% in the long run, because that's the confidence level. Now, what is different if the sample size is larger is you'll see that the confidence intervals are narrower, right? They're more, you're going to be able to estimate something more precisely when you have more data. But this is just a fun thing. I said I always like to do this: change something, and then see if you can get the students to guess what's going to get larger and what's gonna get smaller. And you may have seen this when I open this up. We can do a confidence interval for a proportion. I'm not going to open up that one just for preservation of time. But what I will do is we have two for hypothesis testing. So one for the mean and one for the population proportion. So I'll open up the mean. So what we're going to do here, same thing, define the population. I'm going to choose normal. It's got a mean of 100, standard deviation of 15. And I can say, well, what's the value we're testing under the null? So in this case, it's 100, which for this example, it's true, right? The mean is truly 100. And I pick sample size, and I am going to, and I can do I want to base this on the Z distribution or the T distribution? And so if I draw this sample, okay, so here's a sample of 25. I've got a sample mean over here, sample standard deviation. Here's a histogram of it. I've got the test statistic, the p-value, and right here I'm plotting the value of the test statistic. So I'm going to do the same thing here where I'm going to animate this. So I'm going to grab 50 different samples, each of size 25, and I'm watching the sampling distribution get generated. And similar to the confidence interval example, what do we expect to happen in the long run is we're going to see that proportion of times you're going to reject the null hypothesis that's going to converge to whatever you've chosen here for your alpha level, right? That's what that means. You're giving yourself a type 1 error rate of 5% based upon choosing that as a significance level. Now, well, and also you're illustrating this idea that this test statistic has a it sort of has a symmetric shape distribution. That t-distribution has that same symmetric shape. And again, I can go and change something. So let's pick an example where the alternative is true. So let's say that the actual mean of this distribution is 105. So I'm testing, is it 100 or not? And it's not. The alternative in this case is true. So if I do this, okay, and so here's the proportion of times I'm going to be rejecting the null hypothesis. In other words, the proportion of times that I will be making the correct decision. And then, of course, 1 minus that is the proportion of times I'd be making the incorrect decision. So now I can illustrate the concept of type 2 error and power. And same concept, go in there and change something. So you might say, well, what if instead of a population standard deviation of 15, what if it was 30? And what you should guess is, well, wait, there's going to be more variation. Well, when there's more variation, it's harder to estimate something, right? So it's going to be harder to be led to the correct conclusion if there's more noise, if there's more variation. And so here you'd see that this proportion of, so the number of times or the percentage of times I'm making the correct decision, rejecting the null hypothesis, is getting smaller now that I make the variation much larger. If I went the other way, so I'll go down to get really small here, 5. Now look at this. I haven't even had one mistake yet. 100%. Is it going to happen eventually? Oh, there we go. I got one that I made a type 2 error. Okay, let me just check in, Ross. We're doing it. I don't see any questions coming in, or at least you're answering them along the way. Oh, this is one of my favorite ones here, demonstrating regression. Okay. So in this tool, make this stuff a little larger here. So you can basically bring in your own data or work with, define it here. So I'm going to define where the intercept is, where the slope is, what the level of correlation is. And I can actually click on this graph and add some data values if I want. So I'm just going to put a bunch of data values in. Okay. Now let me open up some things here because I want to see a bunch of pieces of output. Okay. Make this a little bit bigger. Okay, so what I'm going to do, well, so there's actually a handful of things you can do here. One is you can ask the students to fit their own regression line. So I can come over here. Over here is my residual graph. So, whoops, I just added some points there. Didn't mean to do that. That's okay. So I can go in here and fit what I think is a line that goes through the data. And then if I want, I can say, well, fit the least squares line, and let me see how close it is. Oh, that's pretty good. Okay. The Kevin squared regression line did almost as good as the least squares regression line. Now over here on the right, so now you're seeing the ANOVA table, right? And you're seeing the residual plots, you're seeing the sums of squares, the F statistic, the p-value. Now I'm going to turn off, get my line out of there. I'm just going to keep the least squares regression line. Now, every time I draw a sample, it's going to draw a sample of size 70 from a population with those parameters. And every time it does so, you're going to get a different set of data. And over here on the right, you're going to see a different set of output, right? For the R squared, the ANOVA table, the parameter estimates, the test statistics, the p-value. And if I keep on doing this, now I'm going to speed this up again. Let's do 50 at a time. Okay. Now, what concept are we illustrating here with those red lines? Well, each of those red lines are the fitted equation from each sample of data. Well, we're basically creating the confidence interval. That's what you're seeing there. And what's nice about this is this helps illustrate the concept why the confidence interval is the most narrow in the center at the mean, and it gets wider at the edges because you can think of it almost like a little seesaw, right? As it starts alternating up or down, it's going to be have the most variation at the edges. Now, there are other things I could plot here instead of just the line. So under this red triangle, I could do things like, well, let me plot the sampling distribution of the slopes. So basically here I'm getting the beta 1 hats. And so every time I draw a sample, so what concepts am I illustrating here? Well, the sampling distribution of the slope has a symmetric normal distribution, which is why we get to use that. Well, we're technically using the t statistic because we're estimating the error, but the same concept is you're saying this idea of how things kind of start approaching normality. There's so many places in statistics that that happens. Um, I used to have a professor when I taught stat theory. He would say this about 3 dozen times in in the course. Would say we all need to thank God for the central limit theorem. So you can pick all sorts of different statistics. Like let's see, how about I can do the p-value um, for the slope. Okay, now as I draw the additional samples. Oh, sorry, let me get this back to the beginning here. Okay, so I'm going to pick, actually, I'll do the t ratio here. So I'm going to see that t-test statistic. And again, I'll speed this up. I'll do 100. Okay, so now you're seeing that t-test statistic. And yes, that's basically creating the t distribution. That's how that behaves. Now, what's also cool up here is I like this tool because you can illustrate the concept of influence and leverage. So for example, I'm going to put a point right there. If I grab that point, oh, hold on. Be careful when I grab it. Oh, I often do that. I gotta grab the point. Ah, hold on here. You don't grab it. Oh, there we go. Okay, so now this point on the edge, I can illustrate that when that goes up and down, the same thing if I go to this side, you can show how that one data point, how much influence that has on the fitted regression equation and actually the results of the test statistics. So if you look over on the right, I can move this point very easily to where the result is insignificant. But if I bring the point in the center and move it up and down, yes, I can see that equation slightly moving up and down, but the slope isn't changing at all or very little. I'm not able to drag it perfectly straight up and down. And you can see that that p-value is not changing that much at all. So this is a great way to illustrate the impact of outliers in terms of what kind of influence do they have on the results. So again, I really like this this concept. And again, same thing, you could say, well, let me look at this if there's a lot more variation. Okay, or you can drag around these parameter values here, right? Changing the slope. So that one's really fun. You might have seen this when I opened this up. We also have something, same thing for ANOVA. And so this is where you can define, here's my ANOVA table over here, and I can move around the population means for these groups. I can change the sample size, how many how many observations are we taking within each group, and and consider different means and see how that ANOVA table on the right is changing. And this is similar to the regression one, is I can start looking at things like the sampling distribution of the test statistic. And so I can start to sort of simulate different what if scenarios by considering the null is true or considering their differences in the mean and seeing how that ANOVA table changes. All right, so we also have a set of, well, let me just check. Okay, looking good on questions coming in. Thank you, Ross, for handling. We also have a set of calculators, and what these are useful for is if you want to sort of do things by hand, so to speak, or it'd be like it's like basically using a calculator, right? So instead of running the analysis in one of our platforms and getting the output, we sort of want to manually put in values for the sample statistics we're getting. So I'll do a confidence interval for the mean. So you can either bring in some data, or what you most likely would be using this for is you're typing in summary statistic values. So when you open this up, you basically just get this little calculator for this particular scenario, which is getting a confidence interval for the mean. I can pick either the Z distribution or the T distribution, and you're going to type in your sample average. So let's say I got a sample mean of 10 and sample standard deviation of 3. And this came from taking a sample of size 25. And then when I click the return button, I can change the confidence level as well. I am going to get the confidence interval. Well, I'll see the standard error. I'll see the lower and upper limit, as well as the value from the T distribution I'm using as the multiplier, and then a visualization of that confidence interval. So same concept, change something and see what happens. So I say, well, what if instead of the sample standard deviation being 3, well, what if it was twice as big? What if it was 6? And you're basically asking your students, can you guess how that width of that interval is going to change? And look, you saw it got much bigger. I can drag this back. Okay, so of course it got wider because there's more variation, right? I'm not going to be able to estimate the mean with as much precision when I have more data. So same thing, or change the classic, right? Change the confidence level. What if it was 99%, or what if it was 90? This one I noticed you can trick students a lot, because when you go and be more confident, sometimes they'll guess like, oh, the interval's getting narrower, and you're like, oh no, if you think about it, it obviously is going to get wider because you have more confidence that you're correct. I always used to give that analogy. I would say, oh, imagine you were meeting a friend somewhere and you're telling them like, oh, I'm going to be there between 6 and 6:30, and you have some level of confidence that that's going to happen. Well, what if you said, hey, I'm going to be there somewhere between 4 and 10 o'clock? Like, well, obviously you're going to be a lot more confident that you can get it in that wider interval. So that was for the mean. We have one for the proportion as well. And we can do confidence intervals for comparing means or comparing proportions. So I'll do the one for the mean. So let's say we have a sample mean of 10 and a standard deviation 3. That's based on 20 observations. And for the second one, it was a sample mean of 12. The standard deviation was 4. And that was also based on 20 observations. I'm going to use, oops. Oh, sorry, I did that wrong there because I should not have put that in. I'll stick with the Z here. Okay. So then I've got values for sigma. So either I'm going to use the T or the Z distribution, picking a confidence level, and now I've got my confidence interval for the difference between the means based upon that. And same concept I've been keep saying, change something, sample size, the standard deviation, the mean, and then see if your students can guess what's going to happen to that interval. What is it going to look like if I change some of these values? Okay. Okay, so here it is. I just switched to the T distribution. Let's see. I think we're about time. I think what I want to move to now is, I guess this might be the kind of the encore presentation is what I'm about to show you. I just wanted to see, just take one last look at these. Yeah, I think I'm going to switch over. Okay, so there's a few other calculators and applets we have. I'll let you explore those on your own, but that sampling I gave you gives you the idea of how they work. Okay, What I'm going to do now is I am going to open up our new LearnBot. Now, if you go to the marketplace, I'm going to bring back the web page here for the marketplace. You're going to find this add-in here called the LearnBot. I'm going to click on this, and the same thing, you basically just download it and then drag it onto your jump icon on your desktop. And when you do that, what you're going to get is, let me get back to, I got this set up here because I have some questions already at the ready here. Hold on one second. What you're going to get under the help menu is you're going to have this added where you'll see this menu item called Ask LearnBot. So I'm going to open that up. Okay. Now we could discuss forever what this is doing to what AI is doing to education. But let's see if we can figure out ways that this is going to be really powerful. Okay. So one thing you can do with this LearnBot is just how do I do something in Jump? And this is great because when students, well, we have lots of resources, right? So if students like, oh, how do I do a linear regression? Or how do I make a scatter plot? Or how do I do X, Y, and Z? We've got plenty of step-by-step guides and videos, but you got to go and find it. But with the LearnBot, you can actually just type that in. So I got some questions down here. I'm gonna copy and paste in. So this first one I'm just gonna ask is, well, how do I make comparative box plots? Return, give it a second here. And this is going to come back with jump instructions. So one of them is how do you create comparative box plots in the graph builder, right? So you're seeing the steps. Again, it's even giving you some options of things you can do. And then the other way you can make comparative box plots is in the fit Y by X platform. And so it's going to show you the jump instructions for how to create comparative box plots in the fit Y by X. So what's happening here is this is actually sourcing all of our documentation. So this makes it much easier. So you don't have to sort of scan through to find it. You can just prompt this and it's going to source all the information. It's a combination of written documentation, even transcripts from videos that it's scanning. Now I'm going to keep going, getting a little bit more sophisticated here. So that was just how do I make a box plot? And I just got the instructions. What about this question? Why would I use comparative box plots? What's the purpose of this? Let's see what this one says. All right, so now, Ross, is that large enough on the screen to read, or is it okay? Just I don't even know if I can make that any bigger.
I mean, it on my screen, it's looking just big enough, but I guess it probably depends on how big the screens are.
Yeah, okay. I mean, you get the idea, but now I'm getting an understanding of why would I use a plot like this? Um, and then let me see, I got a couple more questions here. How about this? Oh, I don't have this set up. I'm saying, what are some challenges in using comparative box plots? Okay, so now I'm getting sort of some things to keep in mind when I'm doing comparative box plots, how you can see things like they're influenced by outliers, the sample size, I can get some misleading results for various reasons. And so that's popping up like that. I'm going to go through a couple so you get a sample. Um, Another category I found is where you can ask the LearnBot, like, how do I interpret some results? So for example, how do I create a scatter plot and how do I look at that scatter plot to see patterns and features in the data? So I'm going to get the instructions of creating a scatter plot. There's a couple of ways you can do it. You can do it in the graph builder, the fit Y by X platform. So I'm seeing all of those options. And then now it's describing the things I should be looking for in the data when I'm looking at a scatter plot and what that might mean. I got a couple more here. Okay. I'm gonna put this one in here. I'm conducting a two-sample t-test comparing means, and I got a p-value of 0.06. Should I conclude that there is no difference in the means? This is always that thing where, you know, you get a p-value so close to the critical value that you're like, what should I decide? Well, this is going to give you the kinds of things to think about, right? It's not just a binary yes or no. It's going to talk about, well, you'll see kind of what pops up here on the screen is I'm going to see things here on. It's going to talk about like practical significance, statistical significance. Well, that might be a significant result at one significant level, it might not be at another. Here's one was I'm going to get a little more sophisticated here. Oh, no, I'm going to do one more. Hold on, before I get more sophisticated. Here's one is I'm going to do stepwise regression. So which stepwise regression methods should I use? Forward or backward elimination? What are the differences? And I am going to get a discussion of how both of these methods work. As you can see, there's advantages and disadvantages being shown. Now I got a little table, so it's kind of talks about how that works. What are some scenarios where one might be better than the other? And I'm even going to get some instructions on how to do it. I typed this one actually in before we all got on the call. I fit a full factorial model in the fit model platform. Results came back with no p-values. Why is that? Well, basically what's going to tell me is it's going to come back and it has no degrees. I fit either more terms or as many terms as there are data points, and I've got no degrees of freedom for error. The sum squared as error is going to be 0. And then now it tells me what I can do to fix that, either changing the model or collecting more data. And I'm going to type one more in, and then we actually might open it up. Let's see here. Okay. So this one I'm going to type in is, so I'm doing a multiple linear regression analysis with 2 variables. If I fit 2 separate linear regression equations with each variable individually, they both are statistically significant with a p-value of 0.01. So if I fit one linear regression model, that term is like highly significant. If a separate linear regression model, that term is highly significant. However, when I try to put both terms in the model, so when I try to create a multiple linear regression model with both of those variables, the p-values for each are not significant. What is going on? And I'm assuming many of you do know what's going on, so I'm going to submit that and see what's going to come back. Multicollinearity, that's the problem. So it's going to talk about reasons why p-values are changing. It's going to give me methods for checking for multicollinearity, like looking at the variance inflation factor. So I'm going to see some jump instructions in there, and maybe even giving me some ideas of how to address this. So things are like, well, picking one of the predictors instead of both, or using other methods like principal components. And the last one I'm going to type in is, and this is maybe more useful for a commercial audience, not an academic audience, but you can ask it things that are, say, how do I solve a particular problem? So in this one, I'm typing in, I'm trying to design an experiment to study the factors that may affect oxide thickness in semiconductor wafer manufacturing. So I got to figure out, like, what are my candidate factors I should think about for designing the experiment. So I'm asking, what are some possible factors I should consider for the experiment? So now it's going to go out and source, well, how does this semiconductor process have when you're growing an oxide layer on a wafer? Give it a moment here. So this stuff is going outside of jump. So it's going to talk about things like controllable, uncontrollable factors. And notice here's what we got: temperature, time, gas flow rate, gas composition, pressure. So it's giving me and what it thinks that could possibly do. So here's another one: material properties, right? Is it a P-type wafer, N-type wafer? Dopant concentration, equipment. So this is a little more suitable for, said, for commercial people who are actually solving a problem. Maybe this isn't that great for academic. Though actually, maybe this could be like, let's say, um, well, you know what? I do this a lot when I teach. In fact, a lot of our case studies, enhanced data sets do this. Is after you analyze data, a common question is to ask is like, what other data would have been useful to collect, or what other things could we look at? So if you kind of approach that um, in a problem, then maybe that could be relevant. So um, let's say you study the data on voting rates, in say presidential elections by different demographics, and you have a certain set of variables, and you're looking at the data, and then you might, want to ask the students like, well, what other variables, what factors may influence voting rates in U.S. presidential elections? So you might say, I should say what demographic factors, demographic factors. So let's say you did analysis and you were just looking at, say, age and gender. And a question you might finish everything up with is, well, what other things could be affecting voting rates? And let's find out. Well, we may have just looked at gender and age. That's probably going to pop up, I'm sure, as one of them, right? So there's our age, education level, income level, race, ethnicity, there's the gender, marital status, okay, geographical location, right? So this is a thing where you get to have, I always like to do this with problems. I always like to almost finish everything I would do with students to say, okay, what would you do next? What additional data would be good to look at or to collect? What other variables could be helpful? And so if you kind of approach that in your classes, then this could be useful to kind of explore that as well. Um, I'm looking at can the bot help with assumptions, what they are for a specific? Let's type something in. All right. Let's type in, okay. What assumptions should I check when doing one-way ANOVA? So I'm just picking something here. And let's see what it says. Okay, so it's going to tell us the assumptions, right? Independence, normality of the residuals, uh, equal variance, and you see it's even showing some jump, where to access that in jump. Well, so you go to the jump marketplace. Bring that back up. So if you just type jump marketplace in Google, it's going to be the first thing that's going to pop up. Go to the marketplace, and here's the student menu that I was pointing out if you don't already have that, and here's the LearnBot. But you may take a look at some of the other items we have. And this is really important actually to know about, because this is where not only do we create these, but some of our users create these, where there's some statistical method that we don't have actually built in yet as one of our platforms, but an add-in will get created. In fact, that's somehow in creating a new method, we sometimes will start off with an add-in, and then you can download that add-in and have that capability. For example, this one here, this Torch Deep Learning, this is these kind of very complex neural network models where you can predict uh, outcomes based upon patterns and images. And so that's an add-in that you can create. I don't know how many in total in total we have there. Ross, if you know, you can certainly share, but I would imagine it's a few dozen at least. Um, all right, I don't see anything else for questions. Ross, looks like you've been handling everything. I'll wait a minute or two to see if there's any more. Otherwise, I think we can wrap this up.
Great. Thank you, Kevin. Yeah, we've been answering questions as we go along here. And yeah, as you mentioned in the chat when you were showing some of the tools under the student menu, those teaching applets, and asked if folks were familiar with them or had been using them, we got a lot of no's. So I'm glad that folks are now aware of that big collection of tools that they can use. And I'll just, reiterate, I think, what a great tool for the classroom the LearnBot is. Kevin, you put it through its paces a little bit right here. I've done the same, asked it all kinds of questions, even tried to do it without punctuation and without correct statistical terminology and all these things just to see how it handles how, a student would actually probably type questions into this. And it really does a pretty good job. I mean, certainly, it's a large language model, so everybody should just be aware that it's, as accurate as large language models often are. And you'll notice at the end of every response, it says, this is generated by an AI model, and of course might contain errors, inconsistencies, or outdated information. But, that's not a feature of the LearnBot. That's a feature of these large language models in general. But, with that said, I mean, really is a powerful tool.
Well, I'm gonna test it right here. I'm gonna say, what are some good ideas for what I could eat for my lunch after this webinar? Let's see. Let's
Uh,
see.
I haven't had lunch yet either, so we'll see if
Uh,
we both have the same thing.
oh, okay. No, sorry. It's gonna help me with statistics. It's not gonna help me with my lunch.
Yep. So there you go. Then it also is good to know that the version embedded in Jump is just going to stick to the topic at hand and hopefully help your students maybe avoid distractions if they start trying to interact with it for other things. But yeah, it doesn't look like any more questions have come in, Kevin. So thank you
Okay.
for yet another informative webinar. And we hope to see you all at another fall 2025 webinar in the coming weeks here.
All right. Awesome. All right. Cheers, everyone.